All right, welcome. Today, we're going to pull back the curtain on the world all around us. We're diving into the incredible and honestly, often invisible processes that turn a raw chunk of metal into the complex, precise objects we use every single day. So let's get into it and follow this amazing journey from metal to masterpiece. I mean, really think about it. Your car's engine, a wrench in your toolbox, maybe even the frame of the chair you're sitting in. They all started out as something, well, shapeless. So how in the world does that transformation actually happen? That's the exact journey we're on today, from a formless blob of material to a functional work of art. Our journey kicks off with one of the oldest and, let's be honest, most dramatic ways to shape metal. You melt it down and pour it into a whole new form. This is the ancient and totally powerful art of casting. At its core, casting is beautifully simple. It's kind of like making a jello mold, right? But, instead of gelatin, you're using metal heated to thousands of degrees. You make a cavity in the shape you want, you pour in the liquid metal, and you let it cool down. This process gives us the rough, initial shape of our part. But as we're about to see, there are ways to make even this first step incredibly precise. But hold on, casting isn't just about pouring metal into a simple sandbox. Nope. There are advanced techniques, like this one called shell molding, that let you create much more complex shapes with incredible precision right from the get-go. So how does this whole shell molding thing actually work? Well, it's a pretty cool step-by-step process. First, you make a pattern. Then, you use that pattern to create the two halves of a thin sand shell mold, which you then bake or cure with heat. After that, you clamp the two halves together, pour in the metal, let it cool, and then you just break the sand mold away to reveal the finished part. Simple as that. But here's the thing, you can't just scoop up any old sand from the beach. The mold material itself is a whole science. It needs porosity, that's a fancy way of saying it has to let hot gases escape so they don't get trapped in the metal. It needs refractoriness to handle that extreme heat without, melting itself. And it needs cohesiveness and plasticity to hold all those fine details together. The real takeaway here is that even the sand is a piece of high-tech engineering. Okay, so melting is one way to do it. But what if you didn't have to melt the metal at all? What if you could shape it while it's still solid? Well, that's where you use incredible amounts of force in a process we call forming. And on this slide, you can see the two giants of the forming world. On the left, you've got forging, which is basically a high-tech version of a blacksmith with a massive, ridiculously powerful hammer just beating hot metal into the shape you want. And on the right, you have rolling. Think of that like a giant industrial rolling pin that squeezes and stretches metal into things like sheets or bars. Let's zoom in on rolling for a second. This diagram shows a three-high rolling mill. See how the workpiece can be passed through those top rollers in one direction and then right back through the bottom rollers? This process squeezes the metal, making it thinner and longer with every single pass, efficiently shaping it into things like steel beams or plates. All right, so we've cast or formed a rough shape. It's a good start, but it's not perfect, not yet. Now we need to get really precise. We need to add bolt holes, create perfectly smooth surfaces, and get the dimensions perfect down to the thousandth of an inch. Welcome to the world of machining, where we literally carve metal away. One of the most fundamental machine tools out there is the lathe. The key concept here, the thing you gotta remember, is simple. The metal part you're working on, what we call the workpiece, it spins at high speed. Then, a stationary cutting tool is moved into it, carving away material to create all sorts of cylindrical shapes. And now, let's flip that idea completely on its head. This is milling. In a milling machine, the workpiece is held still while a cutting tool with multiple teeth spins like crazy, carving material away as the workpiece gets fed into it. So let's recap. Lathe, the part spins. Mill, the tool spins. That fundamental difference is what allows for an incredible variety of shapes. And believe me, it gets even more detailed. Even within just milling, engineers have choices to make. This table compares two techniques, up milling and down milling, and it all comes down to which way the cutter is spinning compared to how the part is moving. That changes everything, from how the little metal chip is formed to the final surface finish. As you can see, down milling usually gives you a better, smoother finish. It's all about picking the right tool for the job. So we've cast, formed, and machined our individual parts to perfection. But most complex objects aren't made from a single piece of metal, right? So how do we join them all together permanently? Two really common methods are soldering and brazing. They might seem similar, but the crucial difference here is all about temperature. Soldering is the lower temp process, which makes it perfect for delicate electronics. Brazing cranks up the heat and uses stronger filler metals like copper alloys to create much stronger joints for things like plumbing pipes and heavy-duty tools. But for the absolute ultimate bond, you've got to go with welding, which actually fuses the base metals themselves together. And getting this right requires incredible control. I mean, even the type of flame, which is determined by the gas mix, is precisely engineered for different metals. It's pure chemistry in action, and just one more step in this whole quest for a perfect part. Okay, now for a little dose of reality. In every single one of these processes we've discussed, things can and do go wrong. Manufacturing is pretty much a constant battle against tiny little imperfections or defects that can totally ruin a part. Let's rewind back to casting for a minute. A classic defect is something called a blowhole, and it's exactly what it sounds like, a small bubble or cavity that got trapped inside the metal as it was cooling down. And that tiny bubble can be a huge problem, creating a weak spot where the part could just crack right under pressure. So why does it happen? Well, remember how we talked about needing that porous sand that can breathe? If there's too much moisture in the mold, it turns to steam. And if that steam can't escape through the sand or out through special vents, it gets trapped, creating a little void in your finished part. It's this incredibly delicate balance of physics and chemistry. And guess what? We see the exact same problem pop up in welding, but here we call it porosity. Again, it's just tiny pockets of gas that get trapped in the weld as it solidifies, turning what should be the strongest point into a potential point of failure. The causes here are all about precision and cleanliness. A damp welding rod, moving the torch too fast, or even a little bit of rust or grease on the metal can release gases that get absorbed into the molten weld and then trapped forever. It all comes down to one thing: preparation is everything. And you know, this quote from our source material really just sums it all up perfectly. Perfection is the goal, but the reality is a constant process of control, inspection, and problem solving. Manufacturing isn't just about making things, it's about making things right, over and over and over again. So, from molten metal in a mold to the forceful squeeze of a rolling mill, the precise cut of a lathe, and the fiery bond of a weld, we've seen the journey. The next time you grab a metal tool or look under the hood of your car, I hope you see more than just an object. I hope you see the hidden journey of fire, force, and incredible precision that brought it to life. Thanks for joining me.